Okay, before we begin, I wanted to draw a picture of an individual trace. And I'll put something like that on there. And what I'm drawing here, this is an X location. I've got time on this axis. I have a hammer blow. Hammer blow that's on a plate, and it generates a waveform that looks like this. Add this to the thing. Right? So this is called the source time history. When does the source start? Starts at t equals 0. Okay. It's also called this whole thing here is called a waveform or a wavelet. All right? And the seismogram itself is basically, you put the wavelet, basically put the wavelet on the time of each arrival. So this thing is what we record. We could also simulate the data in a computer with this same approach. So here's the time pick. And there's another one down here. Okay? Now, if we were to look at the amplitude of the waveform, this is 0. Right? This amplitude right here is 0. There's no energy or amplitude that occurs before what we call the first arrival. So if we had a source over here and we were sending energy over to here, obviously the first arrival would not occur at time 0. There's some kind of time delay between when the source occurred and when the first arrival occurred. This thing here could be a weaker arrival, like a reflection off of that. Or it could be simply an arrival that traveled a longer distance in the same medium. Okay? The amplitude of the arrival is this value here. Here's 0, and here's the amplitude. So you can imagine I could take this waveform and plot it just like I did here. Okay? Where this is positive, this is negative, this is amplitude, and this is time. And so this would be called the peak amplitude, or maximum. Obviously this would be the minimum. Now, we call this a trough. Okay? And all it means is that there's a negative deflection of the seismogram effect. So depending on your sign convention, you can imagine a pressure wave, right? If it's compressing, it could be a positive amplitude. If it's dilatating, obviously we could take some kind of measure of the average amplitude, right? But we can't really do it by just taking a straight average, because what would we get, roughly? We take a straight average of the waveform, what do we get? 0. So we have to do something like an average absolute amplitude, or we could do something like an RMS amplitude, which is basically the sum of the squares and the square root of that, divided by the number of samples in the waveform. Now, if you remember this seismogram, you know what, can I get to, do I have, I don't know if I have that. I want to get that data. Let's go to this. Okay, this is a real waveform. And it kind of illustrates this concept. Again, it's a multi-channel waveform. And if you notice the amplitudes here, so this would be 0 right here. And this represents the deflection in the positive direction. Sometimes we fill with a darker color the deflection in the positive direction from the deflection in the negative direction, which we leave white, okay? So those pictures that you were looking at, the original waveform had dark and white on the seismogram, right? The dark could be the positive amplitude, the white could be the negative amplitude. So you can see what we're doing here, though, is we're basically picking the first arriving energy, okay? Now, it gets a little tricky in here, right? I mean, you can see that there's actually a deflection up here. And getting that position right is complicated, okay? Now, if we had a source time history that was a perfect waveform, something like this, so an impulse at time t equals 0, then it'd be no problem to pick that again. But because we have a waveform that's spread out, sometimes that deflection goes into the noise. So even if you have a nice break like this, imagine that this thing actually slopes. There's some kind of slope that goes into this. Imagine that there's a level of noise. Any physical arrival will have noise that's going on, so we might not see the first arrival until that point. So travel time picking is not just necessarily automatic. And a lot of it depends on how you plot the data. Right? There's a real art in geophysics to plotting the data in the correct way. For example, suppose, does everybody understand clipping? Does that make sense to you? That the way we plotted it, we don't see any of this really big amplitude. This thing stops right here. Well, that's not physical. That's impossible. You cannot just have a flat top like that. So this waveform would actually probably, not way up here, but it would probably deflect a lot more, all right? Why are we plotting it that way? Why are we looking at the deflection? Because we're interested in the first arrival. And we want to plot as much deflection here as we can so that we can pick this very subtle transition from 0 amplitude or noise amplitude to a real arrival. If we didn't do that, if we plotted it normally, we would probably get a pick later, okay? And if we get a pick later, the problem is that our time delay is shifted. And you get the wrong average velocity. But if we measure the slope of the event, pretty much anywhere on this waveform, from say here to here, or even over here, do we get the correct velocity? Does the slope really change? Does the slope change? What? No idea? No idea. All right, let's take, so here, that's good. I like no idea answers because they let me figure out where things are. All right, so here is the slope of the time pick, right? This is time right here. Here's the slope. Now we know from last time that if the wave is traveling horizontally, the slope is related to what? What's the change in distance with travel? Velocity, exactly. So the slope tells us something about velocity. It tells us the velocity. If the wave is traveling horizontally, what information, and we talked about this before, what information do we get about the velocity